Thank you, Andy. So good afternoon, I guess. Good afternoon, everyone. So thank you so much for being here. Today, our webinar is about micromobility as a solution to reduce urban traffic congestion. So I am Xilei Zhao. I'm currently assistant professor in the Department of Civil and Coastal Engineering at the University of Florida. So today's webinar is sponsored by the STRIDE Center. So STRIDE is the 2016 USDOT Region 4 University Transportation Center. So we are a consortium of 10 Southeastern colleges and universities with the University of Florida as the lead institution. So our mission is to develop new strategies for reducing congestion. So we invite you to contribute questions at any time through the chat box or through the Q&A, and we will answer them at the end of this talk. So before we get started, I want to quickly just introduce our research team. So our research team includes me as the PI and Dr. Virginia Sisiopiku, who is the co-PI from University of Alabama at Birmingham, and Dr. Ruth Steiner from Urban Planning at University of Florida. And we also have other student researchers and postdocs and other professors participate or be part of this project, including Yiming, Yepeng, Da, Zhao, Wencui, Mustafa, and Huan. Okay, so our project is about the emerging travel mode, dockless scooter sharing. So it is a new transportation strategy that enables users to have short-term access to a scooter as needed basis. So since 2019, people in the US took 86 million trips on dockless e-scooter sharing system. As you can see over here, that scooter sharing has shown us very strong and rapid growth compared to traditional station-based bike sharing, and has becoming taking a largest market share in the micromobility space. So over 100 US cities right now have their dockless scooter sharing systems, and including our city, Gainesville, and also Birmingham. So the micromobility has many potentials. So it can reduce reliance on personal vehicles. It can provide better connection to public transit, and potentially can complement each other, and it can offer solutions or options to underserved population by offering discounted programs. And it can also has a potential to reduce traffic congestion by replacing car trips, especially the short car trips, and cut greenhouse gas emissions. So in our study, we are focusing on this problem that because the research in the area of modeling and analyzing the impacts of micromobility on the transportation system operations and quantifies effects on congestion reduction is still very, very limited. So in order to help us better understand this problem, so we aim to examine how micromobility will impact traffic operations and its potential to reduce traffic congestion. And in this study, so we are essentially have 4 different components, including analyzing historical travel patterns of micromobility trips and forecasting micromobility demand. And then we did activity-based traffic simulation, and in the end, we had a policy analysis. So our talk will be divided into 3 parts. So first, I will talk about these first 2, analyzing travel pattern and forecasting demand. And then Virginia will talk about traffic simulation, and in the end, Ruth will talk about policy analysis. Okay, so in order to analyze or understand micromobility usage, the most important thing that we need to consider is what are the data available that can allow us to do such analysis. So fortunately, so we have this kind of general bike share feed specification data, which is called GBFS data, which is open data for shared micromobility. It generates real-time data that is publicly available, so everyone can access those data through public APIs to help us to collect the e-scooter related information throughout the day. So in order to analyze such data, so we need to understand how this data was kind of generated. What's the data generation mechanism and what's the underlying logic? So the GBFS data essentially are showing the location of the available vehicles on in the transportation system. And those kind of data have 3 different kinds of ID generation mechanisms. One is called a static vehicle ID, which is essentially the ID does not change until the service is just taken out of the service. So essentially they have a consistent ID throughout its lifetime. And for the second, so because of the privacy issues, so then we have a newer standards, something called a resetting vehicle ID. So it's essentially the vehicle ID of the vehicle will randomizes after every trip, but it's otherwise static. So essentially, if the vehicle is not being used, it has the same ID. However, as soon as the vehicle is being used, and after its usage, when it reappears in the system, the ID will change. So this is called a resetting vehicle ID in order to preserve users' privacy. And later on, people still feel like it's still not that good. So people come up with a newer idea, which is essentially doing dynamic vehicle ID, which is vehicle ID for all the vehicles in the system randomizes every several minutes. So that's for the dynamic vehicle ID. So the GBFS data only provides information on the available vehicles. So essentially, as you can see over here, so we can only see at a certain time point what are the available vehicle in the system, and this kind of information will keep changing across different timestamps. So we will, from this kind of information from the GBFS data, we will be able to infer people's travel based on such information. So because of there are 3 different kinds of ID generation mechanisms, so we essentially developed the 3 algorithms to extract people's usage from the raw GBFS data. So for the static ID data, so we are developed an algorithm that can essentially extract all records for a unique vehicle ID, and when the information disappears or the ID disappears, we immediately can identify its trip origin. And when the information reappears, we will know this trip destination. So essentially, we have this information available directly to get from the GBFS data with static ID. And with resetting ID, we also developed an algorithm. So essentially, we will know the first record is gonna be the trip destination because it just appeared in the system, right? And when the last record of this ID disappears, so we will know this is gonna be the trip generation of the next trip. And for the dynamic ID is getting more complicated and tricky, as you can imagine, because we will only know at different timestamp where are the location available, and it's at the next timestamp, if 2 vehicles kind of disappeared from the system within certain buffer, we will be able to kind of infer this is gonna be like a trip generation. And if there's at another timestamp, there are 2 new available vehicles reappear in the system, we're gonna infer it's gonna be a trip attraction over there. So essentially, we're looking at those kind of the spatial location, and based on the temporal data, we developed an algorithm to extract trip generation and trip attraction separately. So essentially, with static ID, we will be able to infer OD pairs, origin destination pairs. However, for the resetting ID and the dynamic ID, we can only infer separate trip generation and trip attraction. We cannot link the trip, which definitely can preserve the privacy compared to the first algorithm, first static ID. However, we also lose some information over there. So for the different algorithms, we have different errors. So the first one is going to be the most accurate and only has some GPS error issues. But if and nowadays the GPS error is relatively small, we don't see that as a major issue. And for the algorithm 2, we have error caused by launch and elimination of the vehicles. And for the algorithm 3, we have the movement of the e-scooter not in use, still creating some errors over there. Okay. So with the algorithms fully developed, the we use the GBFS data in Washington, D.C. from the February 24th to 2020 to March 1st, 2020, to infer how many trips are generated across the time and the space. And we have vendors from bird, jump, line, lift, skip, and spin. So I want to say that, want to note that. So different vendors have different vehicle ID mechanism. And sometimes for even one vendor at the beginning, they maybe have static ID, but after several months, because of the standards change, they maybe switch to a different ID with the time going on. So we have a mixture of all three different types of vehicle IDs in this original data set. So then I want to skip a lot of technical details. I want to just show you what the result looked like. So essentially, we pull out some data from a vendor that has a static ID, which has the most accurate inference result. And we treated that as somehow like a ground truth. So then we apply the resetting ID mechanism and the dynamic ID mechanism on that data and create kind of synthetic IDs and then apply our algorithm 2 and 3 on top of this data to evaluate the performance of our algorithm 2 and 3. So as you can see over here, so we cut the entire space into grids, something like this. So we cut it into grids. So the grids can take on different size. As you can see, very small size, like 100 meter until 1,000 meter. As you can imagine, when the grid size is small, the arrows tend to be larger, but still you can see in general, the R square is larger than 0.7 and the overall sum absolute error is less than 6%. So which indicates our algorithm is performing very well. And if you're interested in using this algorithm, so we already provide open source all our code on GitHub. So I'm happy to, so I can copy paste that link in the chat box afterwards. So you can access this algorithm and apply that to your own GBFS data. And this paper is now being accepted and as press in the transportation research records. So after we inferred the trips from the GBFS data, the next thing we do is to trying to forecast the micromobility demand using machine learning model in order to help us understand how people are using micromobility and how different factors are impacting micromobility demand for policy making. So we are comparing different types of models. We looked at linear regression models, and we also look at like popular machine learning models, including decision tree, random forest, and the boosting model. So here are some results that we have. So as you can see over here, so random forest has the good in-sample and out-of-sample performance, and boosting has the best in-sample performance, but has fair out-of-sample performance, which indicates an overfitting problem. So essentially, from these results, we can see random forest is the best model. And the next thing we did is essentially we are trying to explain the random forest model by using some post hoc methods for machine learning interpretation. So this is like an emerging field in AI. It's called interpretable machine learning or explainable machine learning. So the first technique we used is called feature importance, which is essentially evaluate how different factors are contribute to the prediction capability of the model. As you can see over here, work score is the most important factor that most important feature that impacting our prediction accuracy. And after that, parking meters, hotels, and things like that are all built environment related variables. So essentially, it's giving us a very strong evidence showing that built environment are playing a very important role for micromobility demand forecasting. Then another tool we explored is called partial dependence plot. So partial dependence plot is essentially showing the relationship between a feature under evaluation and our predicted value over here, which is the trip origin demand, so the trip generation demand over here. So the partial dependence plot compared to the traditional linear regression, we all know when we are trying to interpret the linear regression, we can only looking at the beta coefficient, which is essentially showing you what's the magnitude of the change and how is the positive trend or negative trend. So essentially, it's showing you a linear relationship. However, partial dependence plots can help us automatically extract nonlinear effects from the complex machine learning models. As you can see over here, the work score and all those kind of features are all showing strong nonlinearities. And let's take work score as an example. As you can see over here, so when work score increases from 80 to 95, so there is a sharp increase in the trip generation demand, while the trip generation demand remains flat when the work score increases from 25 to 65. So essentially, in very workable communities or neighborhoods, that we can see a sharp increase in micromobility demand. However, in less workable, in this kind of region, even though the work score is improving, still not attracting too many people to use e-scooters over there. So that's a very interesting observation that we get from this, this part of the analysis. So there are some key takeaways from here. So the first thing I want to say is, as you can see, the machine learning models have better performance in predicting travel demand of e-scooter services, and the built environment variables are very important in predicting the demand. And there are very interesting nonlinear relationships between the trip generation and the features, and which requires more studies and understanding in the future. So lastly, I want to say that talk about our decision support tool, which is called Thermos. So essentially, based on the GBFS data, so we developed a decision support tool that allows people to report incidents on the map, and we will map that the availability and incident reports on an interface like a dashboard. And we also have an analytics module can help us examine, how many scooters are following the policies about equity related policies, and parking violations detector and trip pattern analysis. Here we have a short demo, so I will just play that to conclude my talk.
Our platform has two main components. The first one is mapping functionalities, and the second is analytics functionalities. Under map, we currently have built two main functions. One is real-time availability, which allows city officials to visualize the available micromobility devices in the city at a given moment. And the second functionality is incident reporting. This function will allow residents to report crash-related incidents in the city. Imagine someone see a crash between a car and an e-scooter at this intersection, and this person wants to report this incident. The person can come to this platform and click this place and report either a crash or a near miss. And then the city staff can gather all the crowdsourced incidents and map them in the city to visualize the patterns to do further safety analysis. The city staff can also click a certain marker to see the details of an incident. The second functionality that we have built for analytics currently include three main functions. Definitely, cities can build more functions or revise the existing functions that we have built. So the first function is called equity monitor. The usage of this function is to allow cities to see if operators have complied with equity zone policy. In many cities, the city have required operators to place at least 20 or 25% of their vehicles in predefined equity zones. In the case of Washington, D.C., 25%. So let's check the companies Spin and Lyft, how they are doing in the last week of March. So here we can see that the two cities have both not fully complying with the equity zone policy. They have only placed about 20% of their vehicles in equity zone, while the city requires 25%. And let's move on to the second function, parking violation detector. So this function basically allows cities to detect if an e-scooter is parked improperly in real time. If violations happen, the platform will send an email to city officials and also the e-scooter commerce. And the third function is trip pattern analysis. Transportation planners or engineers can analyze trip frequency or length in their city. So let's show the trip frequency across different parts of the city. So DC has 8 wards. We will show the trip frequency distribution in Ward 1 and 4. We can see that the number of trips starting from the 2 wards and ending at the 2 wards differ significantly throughout the day.
Thank you all for your attention. So in the end, I want to just thank everyone for being here. So I will transfer our presentation to the next speaker, Dr. Virginia. Thank you. So I will answer the question in the end.
Hi everybody, this is Virginia Sisiopiku. I hope you can see my slides properly. I'm a professor at the University of Alabama, Birmingham, and I would like to acknowledge the participation and contribution of my colleague, Dr. Dayan from Computer Science, and our students to this part of the work, Jalal and Mustafa in particular, that is describing our attempts to have a traffic simulation of e-scooters using the UAB campus as the pilot site. We really looked at the literature review to identify microsimulators that can model micromobility, and that literature review showed the lack of such off-the-shelf tools. That motivated us to look more carefully on the feasibility of modifying existing platforms to use them for incorporating micromobility options into the traffic network. And the ultimate goal of this effort is to be able to study the potential impact from introducing e-scooters and other such modes on local congestion. So our study area is the Birmingham area, and as far as the history of micromobility here is concerned, we had an initial quick deployment in 2018 of BERT electric scooters. That happened pretty much overnight, but the company did not have a secured business license to operate in the city. So that operation has terminated pretty quickly, but there was an interest, especially because we have a lot of students and a large campus, so very close to the downtown Birmingham area, to revisit the possibility of having micromobility options here on campus. So in 2020, the city of Birmingham started an initiative, a new pilot, to invite e-bikes and e-scooters, which had to be delayed due to the pandemic, but they did launch the pilot in 2021. So we thought we would get some information from there as we tried to explore how we can incorporate some micromobility options in traffic simulation. The model that we used for that, the platform we used for that purpose is the MATSIM. That is an open source agent-based transportation simulation software. We prefer to use that because we could build on our earlier research related to STRIDE Project B and STRIDE I2 projects, where we had developed a baseline model for the Birmingham area. For this effort, we developed new Python programs that generated realistic travel plans of UAB employees and students. And these plans were then fed into the MATSIM model and used to compare traffic impacts with and without the presence of e-scooters, using average speed and traffic volume as our performance measures. Some of you may not be very familiar with Maxim. It is a simulation platform that is implemented as a Java application, and it adopts the activity-based approach to generate and simulate individuals' activities. It is an open source software, and it is designed for large-scale scenarios. And the reason we have chosen it is that, as I said, there were no available other available simulators, but also because that promised that we had car sharing options and so on. So we had some hope that it can do what we were looking for. Maxim has two layers, the physical layer, which simulates the physical environment where the travelers, which we call them agents, move. And this is the micro simulator. And then the mental layer that refers to the model logic that create the agent's daily activity decisions. So the required input files for Maxim are three: the configuration file that contains the parameters that may be modified or tuned, the network file that contains the nodes and links that make our network. For our application here, we use the OpenStreetMap in order to get the network file. And then the plans file that contains the daily travel plans of each agent. Now, each plan has different activities and travel modes, and each activity contains information about the location and the start and end time of the trip. And then the mode determines the mode that is used, such as driving, walking, or using e-scooters in this work. What I should say also is that the Maxim does not have a detailed module to support e-scooter mode directly. So the closest that it provides is the car sharing module. So in this study, we revised this car sharing module to provide support for different types of micromobility travel options, such as the scooter. And then for each one of those modes, we will have some specific parameters. For example, you see here the maximum speed, the passenger car unit, the length, the width of the mode. And then the Maxim subtool mode choice strategy was enabled. And with that, the Maxim considered the different options of the modes and selected the one that provided the best score. For different modes, we configured the parameters for the score function to be different so that the most proper mode can be selected based on the leg length. An example here is that for a 5-minute walk, for example, we would be preferred than driving, but if the driving, if we have to walk for 30 minutes, we'd rather take the car, something like that. So this went into the scoring. As Xilei mentioned, a lot of all this has to do with the data. So we needed different types of data in order to create data plans for our travelers in the simulation. We needed to find origin locations, let's say the home locations, destination locations that would include work, parking locations, classrooms, and e-scooter stations. So we started with conducting a mobility survey of UAV students and employees. We got around 9,000 responses from that. And that gave us an opportunity to get location distribution information for their homes and workplaces, which was important for our modeling. However, those were not very precise because we wanted to protect participants, and we had to take some steps in order to get more precise information. We had information about where the students and the employees would live on campus or off campus. we got information about locations where classes would take place, and also the schedule for classes. That was for a typical Wednesday in the fall of 2020, just before the pandemic. And we got information about entry and exit times, and all this was used in order to have a realistic plan generation for the activities. Parking locations were also important. We obtained those related information from the UAB transportation and facilities, and we used the information for geocoding the API to get the exact location. We proposed the scoring function to balance the importance of the distance from home to parking and say from parking to class. So all these details are provided in our report. With this information, also we added the e-scooter location. So these are locations that coincided with the parking locations for scooters that the pilot program in Birmingham had implemented. So we try to make this as realistic as possible. With respect to traffic, we consider 3 types of traffic for our test site. We consider the background traffic, and that was for travelers that were passing through the UAB campus, where UAB was neither the origin or the destination of this trip. And then we considered student traffic, primarily to go from home to class and so on, or back, and employee traffic generated for employees going to and from work. And with this, we did the plan generation, which is the most important part of Madsen, and that defines the success of the entire simulation. With respect to the scenarios that we ran, we had first the scenario that was the baseline, where we consider no scooters, just the background traffic. And then we had 3 scenarios that involved scooters. The first one had 500 scooters to closely match the pilot e-scooter deployment in our region. And the others assumed an increase in this number of scooters, so that we can see what would be the expected impact if we had even more in our area. Madsen, for those that are familiar, runs with many iterations. We ran 50 iterations for those experiments, and we assumed that over 22.8 thousand students and 20,000 employees use the area, which is close to what is our current population here at UAB. So let me give you a little sample of the results that we got. So in this slide, we see the distribution of trips by mode generated by Madsen for the Birmingham study. And on the left, you will see the baseline conditions. We are a very heavily automobile dependent region here in Birmingham. You can see that 96.5% of our trips to and from campus are by automobile, and 3.5% walking, even without the scooters. When we introduce the scooters, even 500 scooters in the area, then we show a shift of 1.82% toward the scooter mode, 1% from the automobiles, and another 0.8% from walking. And as we introduce more scooters, we saw a little extra increase in the percentage of scooter use, and a little more drop in the automobile trips, but not significant. We also, as we ran the simulation, we obtained hourly traffic volumes and speeds along certain corridors. Here, for example, I'll share the results from corridor along 14th Street South. What you can see here is the comparison between volumes with red showing the baseline conditions with no scooters. And then with blue, you see the scenario 2 that represents 500 scooters available in the region. And what you can see from that slide is that when users can take advantage of scooters, then the traffic volume is reduced during all hours of the day. That next slide shows speeds for the baseline versus 500 scooter scenario. And the results show that along scooters generally increases the speed along the study corridors. And that, of course, has a positive impact on traffic as well. On this last slide of the results, we did a comparison of volumes between baseline and different e-scooter scenarios, like a sensitivity type of analysis. And what we can see is increases in speed are more pronounced during peak hours and when larger shared e-scooter fleets are available. And these are just sample results. We have more, of course, in our report. In conclusion, our study confirmed that the availability of scooters on campus resulted in local model shifts. And when e-scooters are available, traffic volume is reduced. And compared to baseline conditions, the average automobile speeds improve in the presence of scooters. And these gains are even greater when we have peak hours and when we have larger fleets of e-scooters. Our study was successful in demonstrating the feasibility of integrating micromobility options in simulation modeling. And through the effort that we put in, we did some pioneering work on the modification of the Maxim car sharing model in order to allow for the consideration of e-scooters as a possible travel mode option in the generation of travel plans. And as a result of this, we hope that researchers now will have a new tool to study and quantify impacts of traffic congestion to model shifts from private automobiles to scooters. I think I can wrap up the presentation right now and just welcome your questions. I will stop the share and I will invite Dr. Ruth Steiner to share her views and findings regarding policy issues related to micromobility. Thank you very much.
Thank you, Virginia. I wanted to begin by saying that I'm Ruth Steiner. I'm a professor in the Department of Urban and Regional Planning, the University of Florida. I want to acknowledge the participation of Juan Suarez, who recently completed a master's in urban planning and in civil engineering at the University of Florida. So the discussions surrounding e-scooters are of multiple types, and it's important to recognize that as we look at them, that we need to recognize that e-scooters are being implemented into a variety of contexts in every city that adopts them into their transportation mix. States and local governments will have different regulations that facilitate or constrain the usage of micromobility. As a simple example, some will allow e-scooters on sidewalks just like they do bicycles. Other places will want them in the bike lane, or sometimes the user may struggle to find a place within the transportation mix. It is helpful to be reminded of the discussion surrounding the use of e-scooters In particular, the benefits of e-scooters, and I'll go into more detail in this a moment, are often seen as the potential to flip personal car from the personal car mode to the e-scooter to what is seen as a more sustainable mode. I'll talk about that in a little bit in a few moments in much more detail. The goal being, of course, the reduction of net carbon emissions. There's also the opportunity for first mile, last mile connectivity. And as you've seen in, especially in Xilei's presentation, it is being used for connectivity within the Washington, D.C. Context. And a third opportunity and benefit of e-scooters can be seen in the technology and the availability. It's ultimately, there's some point in the future where we think about mobility as a service. It also provides opportunities for data on how people are traveling in certain contexts that might help local government officials to understand how they might tweak transit or other systems to be much more effective. Other concerns surrounding e-scooters include things like economic and climate conditions, managing high volume corridors. I'll go into that in a few moments, as I go into curbside management, regulations and policies. And then finally, in the implementation, what we learn is that there is concern about who is getting access to scooters. They're easier to implement probably in certain land use and built environment considerations. And the advantage of the two presentations we've just seen is that Washington, D.C. is quite urban and quite mixed use and high density of land development, whereas Birmingham is probably a much more suburban type of development. And then there's concerns about interactions between scooters and other modes, including bike shares. Does it reduce the number of people using bike shares? How does it interact with modes? You saw in Xilei's presentation about the question of, is it used to access public transit or is it used as a substitute? And the other part is, ultimately the questions we're trying to understand is how are scooters integrated into the transportation system? In general, there are three major concerns about e-scooters separate from the implementation, which I'll go into in greater detail in a few moments. In general, the general assumption is that they are environmentally beneficial when you consider mode substitution. But at the same time, you really need to think about rebalancing and life cycle cost of scooters. We also need to consider the equity of their usage. The perception has been that because they are electric, they do not contribute a significant amount to carbon emissions. First of all, we really need to consider the source of electricity in any given community. For example, places that have coal-fired power plants as an electric source will have much greater emissions than places that are using a high mix of solar, wind, and hydroelectric power. Other factors that make e-scooters less sustainable include rebalancing, and this is really the crux of the issue. Rebalancing, for those of you not familiar with it, is the process through which e-scooters are picked up by operators, recharged, and redistributed. The cost to the environment is high when they are distributed to areas of low demand, at a distance and far from each other, or far from where they are recharged. The greater concern is that the vans used to pick them up are in essence they're not necessarily energy efficient, and that when you account for the emissions of the entire system of operating e-scooters, in fact, the amount of emissions per scooter may be higher than other modes. Another concern is the scooter production process and life cycle costs. It is estimated that an e-scooter used by many of the providers, when it's in regular use, it lasts around 6 months. Given that they include a lithium battery, which requires significant life cycle costs in mining, transporting, and manufacturing, they can have a significant impact on the environment. The good news is that 95% of e-scooter components are recyclable. The question, however, is, are they being recycled or are they being discarded? The bottom line is that e-scooters are better than the average car, but when we need to consider, then we need to consider what mode they are replacing. They can be used in areas of high usage, such as downtown areas, near universities, near multifamily, high density, and mixed use areas, and over a relatively short distance between a half mile and 2 miles. So thus, while equity may suggest we include them in low income or single family neighborhoods, there may not be enough demand, and the environmental concerns associated with rebalancing may not be addressed. Thus, however, equitability should not be completely ignored. The question really may be, do we have enough demand for both a bike and another issue is this competition, because do we have enough demand for both a bike and a scooter sharing program? As far as the mode shift question comes in, overall, the literature suggests that only about 10% of trips are shifting from car to e-scooter, while 60% are transferring the more sustainable walk mode to e-scooters. Now, this is notwithstanding the results from the Washington, D.C. that Xilei presented a few months ago, where and that's the issue, which is, are they competing or complementing public transit? So in terms of policy analysis, I've long ago learned that when you're doing work, and this was not totally expected when we started this project, although it wasn't completely, did not take us completely by surprise. In 2019, NACTO, the National Association of City Transportation Officials, released a guidelines for shared micromobility. And that document includes both best practices recommendations and the current state of practice. Best practices include topics such as regulating shared mobility, general terms and conditions, scope and operations in oversight, public engagement, mobility data and user privacy, and infrastructure, that is sidewalks, bike lanes, what is the right of way. And the current state of practice includes discussion of vehicle requirements, fleet requirements, data requirements, fees, employment requirements, adaptive device requirements, discounted pricing programs and adaptive device requirements, and finally parking requirements. I'm going to focus much more on the regulatory side and assure you that the best practices can be quite helpful. In terms of thinking about regulatory regulatory structure, the essential purpose of regulation can be seen as a question about safety with regard to the scooter's interaction with the public and safety with regard to the scooter users. In general, the scooter users are, in some respects, using these at their own risk. The focus here really is about the question of the safety of the public and how these vehicles interact with other users in the road. And the cities really need to address the public place of e-scooters. Should they be on the sidewalk? Should they be in a bike lane? Should they be allowed on transit? And generally speaking, when we look, and there's trade-offs, but in general, the guidance of NACTO suggests that the best way to understand some of the questions that I'm raising here is really using a pilot project for up to a year. And the reason for the year is that really allows seasonal uses. Some communities have winters where the scooter usage might be low. Some places have really hot summers where the scooter usage might be relatively low, or you might have seasonal visitors in the community. So really and in that pilot project, the goal should be to address the coverage area. How wide an area will the e-scooters be provided? How do you deal with rebalancing? How much rebalancing do you need? And then really the idea of corral and docking stations. Another concern that really should be addressed in the regulatory structure is that the number of operators. The general guidance is that the number of operators should be limited to a maximum of 3. because it allows for greater administrative efficiency and enough but not too much competition. And in the sense it really allows data sharing with 3 organizations. Once you get to be larger, a larger number of providers, the administrative burden might become great. Although not surprising, Washington, D.C. may be a place for more providers. As Xilei mentioned, she said they have showed 6 different users. But in general, they recommend a maximum of 3, but at least some competition. And in essence, the goal of the operators, the number of operators, is to understand the supply side details. That is when you begin to realize if the usage is low, you need to understand why is the usage low? Is it due to demographics? Is it due to the built environment? Or is it due to the lack of availability of scooters? Another suggestion in NACTO is the idea that you have an Office of Mobility in the city that sort of overlooks and really looks at how micromobility fits into the bicycle and pedestrian planning within the community, how it fits into transit. And so that in a sense, we're working towards what might be a future of much more intermodal and multimodal connectivity. And other things within operations oversight. And the reason for needing to have some oversight is that during the pilot project is that most places are learning the greatest issue is rebalancing of the e-scooters. And sometimes do they end up at the bottom of the hill? Do they end up at certain destinations over other destinations? But once you've gone through a year of piloting, you can begin to figure out how to minimize rebalancing. How do you incorporate equity of providing services, and how do you ensure smooth operations within the entire transportation service? Additionally, it's generally recommended that we engage the public more broadly. NACTO recommends that local governments provide incentives to participate in user surveys as part of terms of conditions for using e-scooters. That is, make it easy, put it right into the app that users are using to access the e-scooters. Additionally, attention should be paid to non-users of the e-scooters to understand if they're not using them because they're not accessible. The other aspect of public engagement includes educational materials to promoting the use of scooters, as well as understanding of the benefits of usage. Communities may also engage the public to overcome the rebalancing challenges, for example, providing incentives for independent contractors to recharge scooters. And this is especially so in low-income communities. It may be important to engage low-income communities to ensure that they are involved in the planning for micromobility. Another great challenges and continued challenge of scooter share and a scooter share is the lack of data accessibility. And for good and valid reasons, micromobility providers may not want to share all of their data, especially not with their competitors. At the same time, local governments would benefit from the information that is collected on the origin and destinations of micromobility trips. Louisville is one of a few cities that have a consistent and streamlined open data service that has allowed for the clean analysis of the scooter share services since they were first adopted in August 2018. Many operators prefer to provide only API data, but local governments should recognize that this data may require computer science techniques, and it may not be accessible to the general public. So in developing data sharing agreements, the city should consider format of the data. Also, it is essential to maintain user anonymity. This can be done by aggregating the data and by assigning anonymized data to each trip. Finally, on the infrastructure perspective, one of the main challenges of dockless micromobility is the propensity to clutter on the curb, especially in high demand areas. At the same time, what has made dockless scooters so popular have been their dockless attribute. Therefore, attending to clutter would mean to address how and where they are placed at the end of a trip. A suggested approach is to wait until the end of a pilot program to identify areas of high demand and areas of constant demand, in addition to hotspots. Considering that scooters are most beneficial when they are ridden in a 0.5 to 2 mile area, the first half-mile areas around hotspots and high demand areas should be allowed for corrals and docking if possible. Placing corrals at adequate distance may also deter too many pedestrian trips from becoming scooter trips, while at the same time being accessible enough to make those half-mile to 2 mile trips. Moreover, considerations on rechargeable docks would help to reduce rebalancing if scooters in these zones were required to be docked at the end of use. Areas of constant demand where usage is significantly lower than areas of high demand should allow for dockless trips, allowing for the service to retain its hallmark benefits. Corridor management can be an area of significant concern. Given that micromobility is relatively new, it is understandable that we may take some time to establish a place for e-scooters in the transportation network. While some recommendations are made by AASHTO, there is little consistent push to establish design requirements for micromobility lanes when compared to uniform requirements stipulated for roadways. One of the challenges of the corridors or bike lanes is the question of whether they're on the sidewalk or the roadway. This may vary depending upon state or local regulations. If they're on the sidewalk, they may conflict with safe movement of pedestrians, especially in areas of high pedestrian usage. If they're on the roadway, they may travel right next, may be interfering with bicycles, and they may travel right next to large cars or heavy trucks without a buffer between them. Additionally, a lack of buffering does not deter vehicles from disregarding these lanes and using them to pull aside from the road. Therefore, it is important for AASHTO to provide more consistent updates on roadway design that is inclusive of micromobility. This could be determined as a function of the demand and land use. Suggestions include the requirement for 1-foot buffers with plastic bollards on roads in downtown areas or university areas. Perhaps the half-mile to 2 mile area could be designed as a reference if for the implementation of such design requirements. If requirements made in this direction, safer scooter usage would be a result. Similarly, curb cuts with cross slopes adequate for wheel size could help prolong the life cycle of scooters. To avoid right hook hits from cars for the safety of micromobility users, a 2-second delayed red signal should be considered in highly trafficked micromobility lanes. So that's where we have understand some of the issues associated with micromobility. I would encourage you to look at the NACTO guidebook. It's quite thorough and adequate. I'd like to thank you for joining us this afternoon, and you can put your many of you have put in questions, I've noticed, in the question and answer. We also ask that you complete our brief 5-question survey at this time using the link in the chat box. That will give everyone, and we will give everyone a minute to complete the survey and submit your questions. And finally, I would like to let you know about upcoming STRIDE webinars on May 9th. We have one on equity, diversity, and inclusion, techniques to diversify and support transportation workforce. And if you'd like to register, and on May 18th, what drivers really think about autonomous vehicles. If you would like to register for either of these seven webinars, I would encourage you to go to the STRIDE website link that we are providing in the chat box. Now we can begin question and answers. Thank you very much.
I think we are running out of time right now. Yeah, it's already 1 p.m. So I saw there's an outstanding question for me. So talking about, the relationship between e-scooters and public transit and its potential to replace car trips. So I want to thank so much for the question from Giancarlo. I'm sorry if I pronounced your name wrong. Yes, so I think all these questions will be answered in detail in our year 2 project, which is primarily focusing on the relationship between e-scooter and transit and how this integrated service can help us improve the traffic congestion in urban areas. So that will be the main research focus of our year 2 projects, where we are finishing up that project right now. We are doing a multi-city comparison between Washington, D.C., Auburn, Birmingham, and Miami. So the multi-city comparison will be presented after year 2 projects ends, which is gonna be October this year. So please stay tuned. So we will be able to answer those questions later. Thank you.
And this is Virginia. We appreciate all the questions that we received. And just for the sake of time, we answered most of them on the question and answer space. So please take a look. We appreciate the great feedback. We know that a lot of you need to go. So if you have any remaining questions, feel free to reach out to us. With that, we'll wrap up for today. Thank you again for attending and looking forward to seeing you in a future STRIDE webinar. Have a great day.
Thank you.
Thank you very much. Thank you.